Okay, so now we'll be looking at this last topic, as I told you, which is generative adversarial networks or GANs, right? So what are these, how they work? So we'll try to see them in the discussion that follows, right? So although GANs were introduced in 2014, they were not very popular in that era, right? For example, if you see the Google trend of people searching for this, so you don't see much activity here, right? But from 2016 onwards, you see the popularity of GANs has increased, right? So what is the general idea of GAN? We'll see from some, we'll try to understand it with some real world example, and then we'll try to map those neural networks, right? So in GANs, you have some real data, right? For example, you can have some real pictures, and then you have a forger. Okay, a forger is actually creating fake data, and it is getting some random numbers, some noisy input, and using this information, it is creating some fake data, right? So there's some real data, and there's a forger who is creating some fake data, and then there's a detective, which actually in technical terms is called discriminator, right? Which we are calling detective. And the job of this detective is to tell which of the two images is fake and which is real, right? For example, if I faded this and this, then this detective should be able to tell that the one on the left is a true image and the one on the right is a fake one. Okay, so this is basically the general idea. Okay, now slightly, if we make it technical, then generator and discriminators are actually neural networks, right? As you can guess. So this is your generator network, okay, which is getting some random noise source as a seed, and it is producing an example, which can be an image or anything else, but we'll be developing that idea with the help of images, right? And you will also have some real data available. And this discriminator is also a neural network, which is solving a two-class problem, that whatever data it is getting, whether it is real or fake, right? So it's a binary classification problem. So it means that this part you already know, it is solving just a two-class problem, nothing else, right? You can implement it with CNN and it's exactly the same thing. But combining it with this part and maybe the whole overall model, it would be a new concept for you. So before seeing more details, first see what is the difference between discriminative models and generative models, right? This is a terminology which is not, you can say, it has been existing even before deep learning. Means this is a common terminology that you will see in machine learning. Okay, so let's first see what is the difference between a discriminative model and a generative model. Okay, so a discriminative model is actually doing classification, right? For example, if you want to discriminate between whether an email is spam or not, so what you do, you train a model, right? And then you feed the text of the email, which is a sequence of words, to your model, and your model will give you a class label that it is spam or it is not spam, right? So it is actually the same thing that we have been doing throughout the semester, that basically you have classes and your model is learning the decision boundary, that okay, on the left side I have this class, on the right side I have this class. So you are actually in discriminative model, we are computing this, that given this, you can say X, which is words in email, you are predicting the probability of Y, which is 1 or 0, where 1 is like spam and 0 is like not spam. Okay, so given X, which is your text of email, you are predicting the label, which is Y. Okay, so in other words, you are actually doing classification by looking at the all the words in an email. The discriminative algorithm is trying to predict whether the message is spam or not spam, right? So this is something we have been doing, you can say, throughout our discussion in the previous weeks. Now, when we say generative model, we are not doing any prediction, right? We train this model, and then this model would be able to generate something, produce something. If you remember, we generated text when we were looking at LSTM, right? So although it was a different approach, but still we were generating something. We were not predicting it is its sentiment or whether it's spam or not, but we are giving text or an image as an output. So if we see it in more detail, so you see here we are not predicting the probability of the class given features. If we say, okay, this is class 1, maybe spam, and this is class 2, maybe not spam, right? So this is say 1, 2. So we say, given this class, how words or other features are distributed in this. So in other words, we are not trying to predict the label. We are trying to see within a class how features, in this case, features are word, how words are distributed. So in other words, a generative model will learn that, okay, if it's a spam, spam would be something like this, some text like this. Not spam, it would be something like this. So in order to extend this discussion, if we compare it with a discriminative algorithm, in a discriminative algorithm, we are mapping, features to labels. For example, we are mapping words to spam or not spam. A discriminative algorithm is doing the opposite of this, right? Means we have the labels, and now we are trying to learn the distribution of this class. For example, we know that this email is spam, so how likely it is to contain these words or these features. Okay, features for some other problem. For this problem, I'm using the terminology word, right? So in case of discriminative model, we are learning the boundary between the classes, whereas in generative model, we are learning the distribution of classes. Like that, for example, in spam, I have this distribution. In not spam, I have this distribution. Okay, so this is what we are trying to learn, that how features or words are distributed in each of the classes. Okay, now with that preamble, we can go back to our main discussion, right? That we go back to how GANs work. So you have a generator which is producing something, and you have a discriminator which is doing classification. Okay, so you give some random noise to the generator which will produce a fake image, and then you have a true image, and you try to feed it to the discriminator which will classify it. Now, once you train it, I will tell you in detail how to train it, but assume it is trained, right? And by the time it is trained, this part of the network would be, you can throw away this part and you can take only this part of the network. Now, if you feed it with something, when the training is complete, it will be able to produce images that will look very real, right? So it means when you train it, as we'll discuss later, and it has been trained, then you can throw away the discriminator and you can use the generator to generate something. Okay, if it is trained on images of animals, then eventually when the training is complete, it will be producing images of animals which will look very real, right? So as I told you, that the generative model, once they are trained, they will allow you to create data. You can create photo or music or text or movie, anything that you like, right? And how do we train them? We basically use, you can say, two models which are competing with each other, which are battling with each other, just like a game. One is trying to beat the other. And in that process, both of them get stronger and stronger, means better and better. And since they are competing with each other, that's why we use this term adversarial, right? Because they are fighting against each other. So now once you have this, before we see more technical details, let me just show you a few output of the models which are already trained, right? So these are all images which have been generated by a network. Means these are all synthetic image. None of these is a real image, but you see they look very realistic. Similarly, this is maybe a work of art. Maybe a model was trained on paintings. So now you can actually use the generator to produce paintings. Like they look very real. And then there's a very famous story. I'm sure you must have heard of it. If not, I'll tell you that uh, a few years back, using GANs and using a code that was available on GitHub. Okay, the model was trained and a painting was generated. So it was a computer generated painting with an open source code which was actually sold for some handsome amount of money, right? You can search for it. It's not fake. It's actually a true story, right? So it's, you see, you download a code from the internet free of cost. You just need a machine to train, and eventually you just produce an image, and you can actually sell it, right? So it is, you just need a machine to train. So you see, this is something very exciting. And just to give you some more motivation that why it is such an interesting idea, that I'm sure you must be familiar with Andrej Karpathy, right? He's a famous data scientist. That so he says that maybe once GANs have progressed, right? So based on your interest, you will have computer generated movies, right? You don't, and the movies that we see today, maybe we'll later be calling them handcrafted movies, right? Because humans are making them. So just like we already use the term handcrafted features, maybe after 5 years or 10 years, we'll be saying, okay, classical, there was a classical time when we used to see movies which were made by human, but today there'll be a common practice of watching AI generated movies. And since they are computer generated, so you can generate as long as you want, right? There's no end to it, right? So you see, this is a prediction, but it is not very far-fetched idea. Maybe in next 5-10 years, this would be possible. We are already generating images, and maybe generating a video is not too far. Okay, so now let's get back to some more technical details, right? So as I told you that there are two deep neural networks which are fighting against each other, and in this process both of them become stronger and stronger, right? So how they are trained, in which order they are trained, that we'll see in a while, right? But for the time being, uh, let's go step by step, right? So what we do is that the generator is taking some noise, some random numbers, and it is producing an image, right? Means some image is being produced, which is some nonsense. We don't know what it is. Then this image is fed to the discriminator, right? Along with images from the real data set. Means when this is your discriminator, you are feeding it with fake as well as real data, right? When you are training the discriminator, fake will have labeled as fake, maybe 1 or 0, maybe 1, it is fake, and real is labeled as 0, means it is real, or whatever convention you are using, right? Now the discriminator knows the ground truth of images. When we say discriminator is in feedback loop, it means discriminator knows which of these images are real and which are fake, right? Similarly, what we do is we connect the generator to the discriminator, means the generator can see how good the discriminator is performing. Okay, so these two are the key statements which I will explain in the rest of the discussion. The discriminator knows the ground truth because you have to train the discriminator that this is real, this is fake. So you tell, okay, this was fake, this was real. And the generator has to learn to fool the discriminator to produce very good images. So discriminator is connected to the you can say, so sorry, generator is connected to the discriminator, so it knows how discriminator is performing. So let's slowly and gradually go towards how things are working. So as I told you, this is some random data. It is generating these images, and the real images are being fed. It is predicting labels, right? But whatever it is predicting, when you are training this part of the network, it can actually see what discriminator is actually doing. For example, if this generator produced 10 images, so it can say, okay, 6 of these were detected by the discriminator as fake, but 4 of them, in case of 4, this the images which were produced, they were able to fool the discriminator, right? So it has this knowledge because this generator can actually see what are the labels which are predicted by the discriminator. Okay, so again, a hypothetical example. Some of the things that I tell you may not happen exactly the way they do, but there's a good example that I found on the internet, so I added it in the slide because it makes things easier to understand, right? So the generator is like a counterfeiter who is printing fake money. Okay, he's a this fake money, and then from the bank you have the real money, and the discriminator is a policeman who has to distinguish between the fake and the real money. Okay, so discriminator, what it would do, if you feed it with a picture of money, you can have a deep CNN here, any CNN that you want, and then if it's a real money, it should say, okay, it's true, it's okay. If it's fake, it should reject it, it should say it's fake. Okay, the generator will be producing fake money. Okay, so since the output is an image. So it is like what we say a reverse CNN, right? We reverse the layers. It means instead of downsampling, we'll have upsampling. We already know how to do that because you have seen semantic segmentation in which the output is actually the produced by upsampling the input, right? So you will have some numbers, you will upsample them, and eventually you will come up with an image, right? So the generator is actually a CNN in the reverse direction. Like you will have something like this, that you will be producing an image. So the depth would be gradually decreasing, and eventually maybe you produce something which is like 100 cross 100 cross 3, which is like an image, right? So we already know that you can upsample and you can use convolution to control the depth. So eventually you will be producing a colored image which has some spatial dimensions which you have chosen, and it will have a depth of 3 because we are producing colored number, right? So this is what generator will be doing. It will take some random numbers as seed, and it would can be implemented with a reverse deep CNN, and it will produce images of money, right? This is what we want. Okay. Now, when we start training, you see we don't have any of these two which has learned anything. We initialize the weights randomly or using some distribution, and then we use back propagation to train them, right? So what will happen in the first round, that since this generator is not trained, so it will create very bad forgeries, right? For example, it is creating something like this and it is saying it is real money, right? So since it is not trained, so it is okay. In the beginning, it will be creating something like that. Now we'll feed it to discriminator. Now you see discriminator is also not trained, right? It is equally terrible at its job of recognizing money. So if you feed it, we don't know, maybe it can say true or it can say false. It depends upon what are the weights, right? Because we have not done any training yet. So it is possible that it is accepted and it is possible that it is rejected. We can't say for sure that what will happen. But the thing is that the discriminator is not trained as yet. Okay. Now, at this point, what you do, you tell the ground truth to the discriminator. Okay. So when the discriminator is looking at this image, and maybe it is saying it seems like it's true because it is not trained yet, then you will tell the discriminator that this is actually fake. And how you tell? By giving the label. Okay, you tell the actual label of that it is fake, it is fake. And at the same time you also show it a real you can say a dollar bill, and then the discriminator will see, okay, the real is something like this because it can see the label, and the fake is something like this. So it will try to figure out, okay, what is, how should I adjust my weights? In other words, it will try to figure out what is the difference between these two. Okay, actually it is not like that, but for discussion we can have, for understanding we can have this example, that maybe the discriminators notices that every time you show it a real bill, it has a picture of a person, and the fake money does not, right? So whenever the discriminator sees a money or a bill which does not have a face, it can reject it. Okay, so maybe with this the discriminator has learned this difference. If there is a image of a person, it is okay. If not, it is fake. So after this step, what will happen? These are, you can say, the bills which were being produced by the generator, but now your discriminator is smart. It will say, okay, there is no person here, so it will reject it. It will say it is fake, I'm not accepting it, right? Now we start round two. What we do, we tell or we share the decision of discriminator with the generator. We'll tell the generator that your images are rejected, right? Means the discriminator is able to detect your images as fake. So you need to do better. You need to step up your game. You need to do something better. And we can tell the discriminator, the generator, that discriminator is looking for faces. Okay, so you should better produce faces in the bills you are producing. So with that, after that information, what will happen? It will get slightly better, and it will start producing bills which are containing, you can say, face of a person. Now, when you feed this to the discriminator, it will say, okay, it is okay, because at this point in time, discriminator only knows that if there is a face, it is real. If there is no face, it is fake. Okay, so discriminator will again again start to accept these as valid, you can say, bills. Now we keep on repeating this. We can again show that okay, this is a real one, and the ones that you are getting, they are fake. So it will again look for some other difference between the real and the fake one. And once it has learned that difference, it will again start to reject these fake images, right? Which had the image of a person. And we'll keep on repeating this. So you see what actually is happening, that we have two feedback loops, because the discriminator knows the ground truth and the generator knows what the discriminator is doing. Did the discriminator label it real or fake? So it knows that, okay, if these are labeled as fake, these are labeled as real, okay, then it means these are okay. This is the job of the discriminator. It needs to change something in these so that it can fool the discriminator. Now, but from the viewpoint of loss function, you see both discriminator and generator, they have opposite loss functions. Now, what we are trying to do in discriminator, we are trying to adjust the weights in such a way that we want to maximize the probability that real data is classified as real. Okay, we want to maximize it. And we want to minimize the probability that fake data is characterized as real, right? So basically real should be categorized as real. We maximize this probability. And fake categorized as real, we have to minimize this probability. Fake should not be categorized as real. So this probability should be minimized, and this probability that real is classified as real should be increased, right? So this is the loss function of discriminator. For the generator, what we want the generator want that the fake image should be classified as real. Okay, so this is the objective of generator, that it wants to maximize the probability that anything which is fake is characterized as real. So you see, this is opposite what I'm saying here. We are minimizing this probability, and for generator we are maximizing this probability. So that's why we say these are opposite loss functions which are competing with each other. So when we'll be training, okay, so you'll be using backpropagation. So when you feed it with real images and fake images, you train the discriminator part, and this is locked. You don't change anything here, okay? And then when you are updating the weights of the generator, then you lock this part, means you do not change anything here, and you backpropagate the errors, that okay, what discriminator is doing, right, to the generator, so that it can update its weight accordingly. Okay, now let's see training a bit more in detail. We say, okay, we are trying to make a GAN which can produce images of celebrities, right, or images of person, right? So we have a data set of faces in which we have faces of different celebrities, and they are all labeled as real. And then we have some faces which have been generated by the generator. Okay, we have a discriminator loss and we have a generator loss. Okay, now let's see stepwise what we'll do. We'll select a few real images from the training set, okay, and we will generate few fake images using the generator, whatever random weights we have. Okay, we'll generate few, you can say, fake images. So we train the discriminator for one or more epochs, depending upon how you have programmed, using both fake and real images. So basically, you are training the discriminator and updating its weight so that it can solve a two-class problem, that whether something is real or fake. Okay, so if it's real, we say output is 1. If it is fake, we say output is 0. So this is what we are doing. At this time, we have real images, we have some fake images. Now we are not using this part. We have these images. Okay, so this is just like a classification problem. You feed this with the label real, you feed this with the label fake, and you see you are not considering this branch. You are saying this is just like a typical classifier, that okay, this is class A, this is class B. You A is actually real, label is real, B is actually fake. So you train a CNN, whatever the loss function you are using, so that it will adjust its weight so that it knows the difference between real and fake. Okay, so here generator weights are not updated, it is locked. Only the discriminator, which we have highlighted, that part is being updated. Okay, now after that, what you do, now you generate another set of fake images. Okay, and then you train the generator, but this time what you will do, all the fake images are labeled as 1, means they are labeled as true. Why? Because you are trying to fool the discriminator. So you see what is happening here. Now you are not using this part. You are using this part, which is highlighted by this red box. It has generated some fake images. But you see what is the label? Real. We are telling the discriminator it is real. Okay. So you will feed it and you will say, okay, for each of these images, what are the labels? Okay, and then you will back propagate the, you can say, loss, so that you can update the weights of generator in such a way that you maximize the probability that fake is actually classified as real, as we discussed earlier, right? So this is what it will try to do. So now you see this will keep on alternating, that you train this, then discriminator, then generator. So this, it takes a lot of time to train again, right? But you will keep on repeating this, and by these opposite competing loss functions, both of these will get better and better, right? Each will learn, this will learn how to produce good images, and it will learn how to actually discriminate between real and fake images, right? So just to give you an idea that if at some point in time you want to implement how, not exactly the source code, but how you should design your solution, right? So suppose we want to make a deep convolutional GAN, which can produce handwritten digits, right? So it means that instead of writing yourself, you can write a computer program which will produce digits just like those in the MNIST, right? So when you talk of the discriminator, so it is a typical convolutional neural network, which is accepting an input, you are applying convolution and pooling, and eventually at the end, you have sigmoid, right? Because we are not trying to recognize the digit. The label is 0 or 1, that whether it is real or fake. So all the images of different digit which you get from MNIST, right? They will all have a label of real because they are actually written by a human. Okay, so they will have the label. So this discriminator is simply a CNN which will give you the probability between 0 and 1 that whether the input is real or not, right? So this is exactly the same thing which we have been doing throughout the semester. The generator would be inverse of it, right? That you will have some random numbers, maybe you can reshape the data, you can perform convolution, reshape data, and then you see here we are upsampling from 7 by 7 to 14 by 14 to 28 by 28, and we are reducing the depth, right? 256, 128, 64, 32, and eventually, since we need a grayscale image, so eventually we get something which is 28 cross 28 cross 1. It means the generator will be producing a grayscale image at the output, right? And once we are training, so you have MNIST data, all the images are labeled as 1, means they are real images, and then you have a generator, and these are labeled as fake, so you will train this part, means this is one step that you will take, okay? And then when you have to train the generator, whatever images it has generated, you will feed them to the discriminator, but this time the label is 1, means you are giving the wrong label, you are saying these are real images. You compute the loss, you back propagate the loss, so the generator will learn or update its weights in such a way that it should actually fool the discriminator so that it thinks these are real images, right? So there's some, not much, but I have included just 3 slides on the code that is available on GitHub as well. That you see, for example, if you are implementing this on MNIST, you don't need labels that this is 0, this is 1, this is 2, right? Everything which is in MNIST, it has the same label, which is 1, because they are real, right? Because we are not trying to solve digit recognition problem. So that's why when we are loading data, we don't care what is the label. We just load data, and the label of all these examples would be 1 because they are all real numbers, right? So this is actually the generator. You see, it has different layers, but we are using upsampling layer, right? Which actually is the reverse of downsampling, right? And eventually your final output it will produce would be like 28 cross 28 cross 1. And if you go to the discriminator, it is like a simple CNN, right? But important is that the last layer has sigmoid activation function with a single neuron, right? Because it is only giving you the probability that if it is close to 1, it means it thinks it is a real image. If it is close to 0, it can say says it's a fake image, right? So you can connect these two using the functional API, and then you can train. I've excluded that code from the slides, but if someone wants, I can share separately, right? Because that's a bit tricky to understand, so I did not include the training part in the slides. We discussed training only at the application layer without actually looking at how you implement that. Okay. Uh, Now you see there are many interesting applications that people have developed using GANs, right? So now you see you have different parameters which you can control. These are all synthetic images. None of these persons actually exist. But now you see that you have parameter like young, that how young you want the image to be. So you can control the age from 0 to 100. Then you can control the smile, right, from 0 to 100. Then whether you want to generate a male or a female image, and then you can control maybe color of hair. Similarly, you can think of other parameters, right? And you see these images are being generated, and they look so real, right? If you don't know they are computer generated, you can actually uh, will not be able to tell if the person exists or not, right? So you see, the advantage is that when we are making some illustrations, when we are making some demos, so maybe if if you use the image of a real person, then you need permission, something like that. Okay. You cannot just use image of any person in marketing or anything else. So one positive side is that if the person does not exist, you have created the image, right? So you have the copyright of that image. Then no one can stand up one day and say that why you are using my picture without my permission, right? So from that perspective, for all such applications, this could be useful, right? And I'm sure you must have heard of this application DeepFake, right? So that was also implemented with GAN, right? Not exactly the same thing. It was much more sophisticated, but the key idea was the same, right? That you can generate a sequence of images, and you can actually create videos or images or even sound, right? Instead of images, you can train it on music. So your GAN can actually learn to generate music, music which is not created by a human, but by a machine, right? So this was you can say some basic introductory level discussion to GANs. So I'll stop here, and if you have some queries, maybe we can discuss those. Thank you.